Hello everybody. In this video we're going to be doing some algebra by combining the natural log and natural exponential functions. We're also going to be finding rules of exponents, and we're also going to be finding derivatives of the natural exponential functions. So before we get to the calculus, let's do a little bit of algebra. So we're going to start at the bottom down here. We want to make sure and memorize some important values that's going to help us in our work with simplifying, rewriting, etc. So let's look at these two important values down here. Okay, I would strongly encourage you to memorize these. Both of these are equal to a numerical value. The natural log of 1 is equal to 0, and the natural log of e is equal to 1. And if you think about it, it has an understood exponent of 1, and so that's going to become the answer right there for a specific reason. Okay. For this first one right here, a graph might help us understand why that value is 0. If I were to graph the natural log function, think back from your parent function graphing background. That's pretty sad. Okay, this point right here is an important point, and that point right there, that ordered pair is 1, 0. And I've attempted to draw the natural log graph. So if my input is 1 for x, hence natural log of 1, then my output is going to be the y-coordinate, or 0. So just try and visualize graphically the ordered pair 1, 0. So if you ever ask what's the natural log of 1, hopefully 0 will pop in your mind pretty quickly. All right, to get this value right here of 1, we can also approach the same graph. It's a natural log graph. So if we look at the natural log graph, let's think of the input value of e. You may remember that e is a number between 2 and 3, and it's close to 3. E is approximately 2.7. All right, so where does e fall if e is my input and it's 2.7? Well, it's going to be to the right of this point right here. So if it's almost 3 and that's 1, I'm going to assume that maybe this is my input of e right here. Now I'm going to look up, find the graph. There it is. Okay, this is the point on the graph that has an x-coordinate of e. Well, what's the y-coordinate that belongs to it? Well, if you were to graph it on a calculator, it'd be easy to find. Okay, but with this visual right here, I'll just share with you, the output is 1. So if you were to plug e in here for x, hence you get natural log of e, the output is going to be 1. That's the answer. Okay, so that's one way to get the important value of natural log of e being 1. Another way to think about it is that here in this little simple problem, you have two inverse operations that are being performed consecutively. Okay, think about the natural log function, and then immediately you have a natural exponential function. Well, log functions and exponential functions are inverses of one another. They undo each other. And when you have these two operations that fall consecutively, the input becomes the output, the input becomes the answer, and the input in this problem is 1. So you kind of think about these kind of falling out, I guess. It's kind of an informal way to say it. Okay, but they undo each other to the point that you're left with just the exponent of 1. So you've got the graphical approach or the inverse approach right here. But these are two important values, and both of which should be memorized, kind of like the unit circle. All right, let's go back up to the top. Rules for combining the natural log and the natural exponential function. All right, this example right here is exactly the same as this one down here at the bottom, except for my exponent is a 2. If I were to find graphically e squared on the natural log graph and go all the way over here to e squared, my output is going to be 2. The point would be e squared comma 2 on this graph. I'm not going to think of the graph for this problem. I'm just going to think that these two are inverse operations. So my answer is just going to be 2. If I had natural log of e cubed, my answer would be 3. If I had natural log of e raised to the 0.25, my answer would be 0.25. These are inverse operations. They follow each other consecutively. My input of 2 becomes my output or my answer. Another way to think about this answer of 2 is some of you guys are going to like the power property for logs. Think about the natural log functions, or the log functions, and the log properties that we have for those functions. We have this as our power. Another way to think about this is to take your power of 2 and move it to the front, because we have a property that says when you're dealing with a log function, you can move that up front. Well, then you can just simply remember that natural log of e was one of those values that you need to memorize, and that's 1. So 2 times 1 is 2. All right, let's look at the second example. We're going to go down in the column. All right, we have a natural log, but then we have a square root of a natural exponential. The log and the exponential are not consecutive. You've got a square root in there. So if I'm going to simplify this, because that's my goal with these problems, is how can they be made to look differently? Well, the first thing I'm going to do is I'm going to remove the square root symbol and make it a 1/2 power. So there we go. We know the answer is just 1/2 because we've seen the patterns. All right, same thing here. The answer is -1. Same thing here. The answer is sin x. Whether you just see these as dropping out or you use the power property from the logs. So we're just looking for patterns. All right, let's look at the second column right here. Now, notice that I've kind of twisted things. I'm not starting with a natural log function. Now I have a natural exponential function with the log function as part of the exponent. So I can't apply properties, log properties, on a natural exponential function. That's okay, we don't have to. We've already seen patterns. A natural exponential raised to a natural log. These are consecutive inverse operations. If you guessed, yes, the answer is 2. Skip down here to the third example because this middle one has something unique. Yes, natural exponential, natural log, they undo each other. If you guessed, yes, your answer is x squared plus 1. Right, the problem with this middle example is the exponential and the log functions are not consecutive. Very similar to what's going on here. I have to do a rewrite. Okay, well, if I just focus my attention on just the exponent, it is a log function where I can apply a log property here. So I'm just going to move the 3 up as an exponent on the 2, allowing me to have 2 inverse operations that are consecutive, allowing me to say that the answer now is 2 cubed or 8. Okay, the rules of exponents. Some things we need to be aware of. All right, from Algebra 1, we know that we have properties of exponents. Okay, well, what I can do with this right here is instead of having terms as far as in the exponent position, I'm going to use a property from Algebra 1 backwards. If I'm adding these 2 numbers, then that must have meant that they each had their own base with the times between them, because we know there's a property of exponents that say if you're multiplying with the same base, add the exponents. So multiplying, same base, add the exponents. That's what it looks like. So this is the kind of a backwards approach to that property of exponents. Right, what could I do with this? If I saw this in print, how else would it look? Well, same base, subtract the exponents. All right, what about this? What's wrong with this? Well, it could be simplified. Several approaches. Most students see this as taking the negative in front of the natural log of x and making it a -1 exponent. So that's how most students would see it. So therefore, we are in the situation that we had over here, where the answer is x to the negative 1. It seems like every year, though, I have students that take a different approach to this, and students will say, okay, well, I have a negative exponent. I'm going to make it a positive exponent by creating a fraction, moving it to the denominator, and making the exponent positive. And think about what just happened here. Okay, these will undo each other, so the denominator becomes x. So I end up with the same thing I have here if I rewrote it as 1 over x. Seriously? Okay. So, okay, quite a bit of background, but hopefully when we get into our work and you see something, you go, what is going on there? Okay, you have a little bit more knowledge now to understand what's happening algebraically. We need to move to now your own paper where we're going to be finding the derivatives of natural exponential functions. So we're going to start with the basic parent function. Okay, we're going to find the derivatives of natural exponential functions. Here's the parent function, okay, and here's a composite natural exponential function, and this is where most of our work is going to take place. All right, so let's find the derivative of just the parent function. So if I wanted to bring in the derivative operator, and we've seen in a previous video with some graphing that the derivative of the exponential is just itself. So e to the x. Okay, and there's actually a baby chain rule in here where we multiply by the derivative of the letter. So we use the derivative operator. Well, what's the letter? Well, exponential isn't a variable, it's a number. The variable is x. But if you think about it, dx over dx is just 1. So we typically don't show this. Okay, so the derivative is just itself, e to the x. All right, well, we're not going to be asked to find this derivative, okay, very often. If ever at all, we're going to actually be asked to find derivatives of composite exponential functions where we have to apply the chain rule. Okay, so let's bring in the derivative operator. Both sides of the equation. So this is the formula we need to memorize. dy over dx equals, all right, if we're finding the derivative of a natural exponential function, it's not a power function, so we can't use the power rule. We have to use the exponential rule. So it's not a power function where the base is x and the exponent is a number. It's a whole different situation. So we're not doing the power rule where we bring the exponent down and subtract 1. Instead, the structure of the answer for this derivative is, okay, the derivative, the answer, contains the problem, e to the u, times the derivative of the inside function, which the inside function is going to be the exponent, okay, when you look at the base of e, times the derivative of the inside function u with respect to x, times the natural log of e. Okay, well, what's the natural log of e? It's just 1. So do we often see this part of the rule, the formula? Nope. Okay, we usually just see this right here. Okay, and sometimes we don't see du over dx. We see it written as e to the u times u prime, where u prime means du over dx. So let's just get to some examples and see what it looks like. So our objective is to find the derivative for each of these. All right, you can bring in the derivative operator if you want. Otherwise, we're just going to go right to saying, hey, I'm finding the derivative g prime. All right, I've identified this as not a power function. I can't use the power rule. I have to use the natural exponential rule. So the derivative is itself, so write that down first, times the derivative with respect to t in this problem, okay, of the inside function, and the inside function is going to be the exponent. So, and I'm going to get it ready for differentiation, so I'm going to write it as negative 1/4 t. I'm on the last derivative, meaning I'm going to find this derivative. This is negative 1/4, and the place we're going to place that is going to be up front. So negative 1/4 e to the negative t over 4. And keep in mind, you could bring this e to the denominator and make the exponent positive t to the 4, or t over 4. Number 2. All right, we're going to go to the prime. It's not the power rule. It's an exponential function. This is the rule, right? The answer for the derivative is the function itself times the derivative of u prime, which is cosine of x. The order of this doesn't matter. I mean, you could put it up front, but I would probably put parentheses around everything. All right, example 3. All right, let's find the prime. The prime is going to have the problem in it. And then I have to show the setup of the derivative of the exponent, u prime. And I'm going to get the exponent ready for differentiation by changing it to x to the 1/3. Next line down, y prime equals. All right, when you look at this right here, now we have a new function here. Now we're no longer dealing with the exponential function. This is a power function where I'm going to apply the power rule to the exponent. So using the power rule, it'll be 1/3 x to the negative 2/3. You can certainly do some cleanup on that. You can create a fraction by putting x to the 2/3 in the denominator with the 3, leaving e to the square, e to the cube root of x on top. Okay, so you could rearrange things here. 4. So 4 is very interesting. To go to the prime, watch out for these tricky problems. E is a number raised to another number. I'm not going to use the power rule or anything, but all I want you to do is see this as a constant. This is just some particular ugly number. Well, what's the derivative of any constant? It's going to be 0. So let's say that you didn't notice, okay, that this was a constant and you went ahead and applied the exponential derivative rule. Okay, so I'm just going to take a second approach here. We should still get a 0 as an answer. Let's just say you went, hey, you know what, that's an exponential function. Let me apply that rule. Okay, so let's go through the motions. You're going to find the derivative of the function, so you write it down, and then you multiply by the derivative of the exponent. Well, if you didn't notice that this was just a constant, I'm hoping you notice right now that this is a constant. Natural log of 2 is just a weird number. The derivative of a weird number, any number, constant, is 0. So if this is 0, okay, then by default, the whole derivative is 0. Okay, move along. Number 5. Okay, notice that I have a quotient. Okay, to find the derivative, I can either use the quotient rule, or since I have a constant in the numerator, I might want to bring up the denominator and use the chain rule. And I think I love the quotient rule. However, I think it'd be a lot easier if we were just to use the chain rule by bringing the denominator up. So that's what I'm going to do. Okay, so now we're starting to get a little more rigorous and combine, you know, some differentiation rules. And so I have to bring it up as a -2. Oh, you see what I did? That's not a prime yet. And I'm not going to edit this video. It's too much trouble. That's just y as a rewrite. All right, so let's find the derivative y prime. Well, the outside function here is 3x to the negative 2. That's a power function. Okay, so I'm going to apply the power rule, and then the inside functions are each going to be the exponential derivative rule. So I'm going to have negative 6, leave the inside alone, drop the exponent to negative 3, okay, times the derivative, and make sure and use parentheses, e to the x minus e to the negative x. All right, so we have a little bit more work to do over here. So term by term differentiation. So y prime equals, bring this down, all right, let's find the derivative of e to the x. So make sure and use parentheses, e to the x minus the derivative of e to the negative x is going to be e to the negative x times negative 1, because it's the derivative of the exponent. And if it's times negative 1, I'm just going to make the adjustment right here and make it positive. Okay, you can do a little cleanup on that, make a fraction, put things in the numerator, denominator, but we're pretty much done. Okay, looking at the time limit here. All right, number 6, going to do this fast and furious. Our objective, find the derivative. Well, let's see. We have a product of two variables. This could be considered our f function. This can be considered our g function. We're going to have to start this with the product rule, and then inside of that will be the natural exponential derivative rule. Everything's ready for differentiation, so I will go to prime. So it's the first, etc. I'm just going to do the setup because I think it's going to be a little more complicated. All right, so we need to find the derivative of this exponential function. Okay, I think I can find that derivative without doing the setup. The derivative is going to be itself times negative 3. So x squared. Okay, I'm going to get a negative 3 from the derivative of the exponent, so I'll probably manage it by putting it up front, negative 3, and then just writing down e to the negative 3x. This derivative is the power rule here, so that's 2x, and that's usually going to be put up front as well. Now what you could do is take out a common factor of x, e to the negative 3x, and that's likely how the author's going to have it in the back of the book. All right, so that's it. That's the derivatives of the natural exponential functions, incorporating it with like our previous rules as well.